All right, so hopefully you noticed that what you guys did on the finance day, that was actually day 5 of this unit previously. So we just moved day 5 up to day 1. And now logistics is technically day 2. So, no. Okay, so this logistics is actually 8.2. All right. So today, the entire day is over logistics. Not to be confused with logarithm. I know that it starts with the same 3 letters, right? Logistics starts with log. Logarithm starts with log. A logistic is not a log. In fact, it is the exact opposite of a log. What it says right here, a logistic growth function is a function that is related to the exponential function. A logistic is a type of exponential. The way you say it doesn't help either. Oh no, doesn't it? Logistic. Is that better? I tend to over-enunciate vowels. Okay, not to be confused with the inverse, the logarithmic function. All right, a logistic is a type of exponential. This function is used when there is a restriction on growth. You logistic, right? Sorry. Okay, when there is a restriction on growth, a normal exponential. Why am I not? Okay. So this is a normal exponential. Exponential. Right? Starts off going along an asymptote and then increases exponentially forever. This represents an exponential growth, okay? A logistic growth function has a restriction on that growth, meaning it starts like an exponential, right? It starts going along an asymptote, starts going up, but then there's a restriction to it and it starts curving to another horizontal asymptote. So yes, logistic is a type of exponential, but it looks a little bit different. There's a restriction on it. All right. Okay, now there are 3 forms of this function. There's the standard logistic growth function. Then there is the base E logistic growth function. And then there is the parent function logistic growth function. So both the second 2 there have a base of E. Now we're going to get more into this in a minute. Well, I guess we could do it now. E, does anyone know what E is? Yes, Caitlin, you're right. E is more important though. Yes, Viva. Euler's number. Yes, Macy, it's Euler's number. It's a now, so E is a constant, okay? E is not a variable. It's a constant. Yes, it starts off as 2.7, blah, 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 right? We really don't need to know what it is. Our calculator has it for us. It's great. E is Euler's number. Whoops. And the reason why Euler's number is so special is because it naturally appears in the real world. So Euler's number. Euler obviously discovered it, right? That's why he called it Euler's number. But it's a number that appears many, many times in the natural world. Now, like Caitlin said, the log with a base of E is called ln. We call this the natural log. It's a log with a base of E. And because this log, this natural log, because it appears in the real world so often, they named it the natural log because it's natural, it appears in nature. because it's so super special, what they did was they created a very, very special abbreviation for it, ln. And because they wanted it to appear more like a log, they didn't abbreviate this as NL, natural log. They just switched the letters around so that, oh my gosh, it starts with an L, so you maybe will think of a log first. ln just means a log with a base of e. That's all it means, all right? Right? Yeah, right. That's funny. Okay, so I just wanted to intro into that very quickly. We're really not going to use ln until the very last problem today, all right? But yes, a lot of logistic growth functions have E in them because a lot of growth in the real world has E naturally, all right? Not all logistic growth functions, though, need an E. Hey, not all of them need an E, right? This first standard logistic growth function doesn't have an E. It's still a logistic growth function, all right? Okay, so let's look at our logistic growth function that does have an E in it. You know, you see, I keep trying to like scroll down with my finger because that's how I do it on my Lenovo, but you have to use 2 fingers on Apple. Okay. So here we're looking at a very, very generic logistic growth function. Looking at this graph, what is the domain of my function? All real numbers. Yep, all real numbers. It keeps going forever to the left and keeps going forever to the right. There are little arrows there that should be there but are not. Now, all logistic growth functions have 2 horizontal asymptotes. Exponentials, in general, always have 1. Logistic goes even further and has 2. What is our first horizontal asymptote on this? Yes, exactly. Y equals 0. This bottom here, and actually that's where this graph is bounded below as well. At this asymptote, that's where the graph is bounded below by the asymptote y equals 0. And then what's our second asymptote? Y equals c. That's our second horizontal asymptote. This is where our graph is bounded above. Now, C is very special. C is what is called, oh my gosh, I forgot the word. Capacity. Oh my goodness. Capacity. No. Shoot. Oh my gosh, this is how today is going. Right? I had such an awful morning. Oh my God, carrying capacity. Basically, all that this thing is the maximum value that y can be. So if this logistic growth function represents, say, a population, and say C was 200, the numerator was 200, it means that the population never goes above 200. That's why it's called the carrying capacity. It can't carry any more. Because that C also indicates your top asymptote, right? So obviously, if you have an asymptote at y equals 200, your logistic function can't go over 200 because there's an asymptote there. And then also in the center of this graph is our point of inflection. It's like our change in direction. You can kind of think of it as. It's where it kind of has the center of its swirl, of its S shape. And that point of inflection can always be found by taking, oh my gosh, this is going to get annoying, by taking your carrying capacity and dividing it by 2. So if our carrying capacity had been 200, we would have had a point of inflection at 100. Any questions so far? All right. Not much. Just like up, oh my gosh, this is so annoying. Just like talking a little bit up here, but you didn't miss any applications. All right, so now this is fun. I'm gonna skip A and B and just go and do the hardest one. Part C. It wants us to find a whole bunch of stuff about these functions. It wants us to find the domain, range, inflection point, symmetry, boundedness, asymptotes, and end behavior. So, first things first, or what would be easiest here, is to start drawing our asymptotes. Where is an easy peasy first asymptote to draw? 20, right? We know that that 20, that carrying case, determines our top asymptote. So I'm going to go ahead and I'm going to draw the x-axis, and I'm going to draw our asymptote of 20. So let's see. We'll have this be our x-axis, this be our y-axis, and then what I'm going to do, because the numbers here don't increase, or I mean the lines here don't increase very nicely. So what I'm going to do is I'm going to say every other line is 5. So down here, obviously at the origin is 0, up 2 lines is 5, 10, 15, 20. So this is my asymptote. Y equals 20. And then we also have another asymptote at 0. This graph, this function hasn't been moved up or down at all because there is no, there actually is no h value. There is no number added or subtracted from our variable in the exponent. So you don't need to know that. It is good to know how to figure out if there has been a vertical shift, but there hasn't been. So I'm going to go ahead and draw another asymptote on y equals 0. Now, those asymptotes tell us what about all the things it wanted us to find? Why is it 0 again? Because it hasn't been shifted up or down. It hasn't been shifted up or down. I know it hasn't been shifted up or down because in the exponent, this is an exponential function. In the exponent, there isn't a plus or minus from x. So if I had instead had this, whoop, oh, where the, okay. Oh, there we go. If I had instead had a +2 here, that would have given me a shift up or down. Okay. But it doesn't, so we're good. So like I was asking, what do the asymptotes tell us about the graph? One of these things that wanted us to list: domain, range, point of inflection, symmetry, boundedness, asymptotes. Oh, well, it does say asymptotes. So I guess we could just immediately write, oh, this is going to get annoying. Asymptotes, y equals 0, comma, y equals 20. But that's not what I was thinking of. What else do the asymptotes tell us? The boundedness, yes. Right here, they wanted us to list the boundedness. this graph is going to be bound above at y equals 20. And it's going to be bound below at y equals 0. Okay. What else can we find? Or what else do you think is a defining attribute to this graph so that we can further graph it? The point of inflection, exactly, Arnon. That's what I would go to next, all right? I have my asymptotes. Now I can find my point of inflection. How do I find my point of inflection? Right. You take the C, I'm just abbreviating point of inflection as POI. You take the C and divide it by 2. Now, what does that 10 tell us? Ten is the Y value of the turning point. What do you think we're going to have to find? We're going to have to find the X value. Yes. So here we're looking for where these two lines intersect, and where they intersect has an X value of 0.231. So that is the X value of our intersection. Yeah. So I have, let's see, this is 5, this is 10, and it's over just a little bit. So that's where my point of inflection is. And I'm going to go ahead, as long as you have the point of inflection and you have your asymptotes, the rest of the line, it really doesn't matter how you graph it. So see, this graph is quite a bit steeper than how I showed it, which is fine. It's perfectly fine. All I care about are the asymptotes and the point of inflection. So are we sure this is faster than solving for X? Yes, when you're not having technology issues, okay, Arnon? For sure it is. Because, and on your Math Excel, it's going to ask for multiple Y values or multiple X values, okay? So it for sure is easier than having to plug it in and solve, plug it in, solve. If you want to solve algebraically, go for it. Just know it's not needed. All right, my goodness. Okay, where'd my pen settings go? All right. So now we still have a few things that we need to state. Let's see, the domain and range. What is the domain? All real numbers. Oh, God. All real numbers. And what's the range? 0 to infinity, and you can never touch an asymptote. No, not infinity. Yes, and you can never touch your asymptotes, so that's why you put parentheses around them. Okay, then what else? Symmetry. When it's asking for symmetry, it's asking for, is it symmetric with the origin, or is it symmetric with regards to the y-axis? If it's not symmetric to either of those, you write none. Does not have any symmetry.
So if the turning point was on the y-axis, it'd be symmetric?
Yes. Oh! No. No. It would be if it did this, right? Then you could fold it over the y-axis.
Yeah.
If the point of inflection was on the origin, then it would be symmetric, and only then would it be symmetric. Okay. Then last but not least, we have end behavior. End behavior, from now on, we're using limit notation. This is to try to get you ready for calculus, okay? End behavior. Now, it's just a different way to write end behavior. It's no big deal. The limit as x approaches negative infinity, what happens to our y value? It approaches 0. So you would say the limit as x approaches negative infinity, our y value is actually a function f of x. So you write, oh, about to throw the iPad. You write f of x equals 0. That's the limit as x approaches negative infinity. And then you go the other way as well. What is the limit as x approaches infinity? Or in other words, what is your end behavior as x approaches infinity? 20. Y approaches 20. So you would write f of x equals 20. That's your limit as x approaches infinity. Why isn't it updating? There we go. Any questions? Okay. Oh my. Now we're going to go and look at some logistic word problems. I'm sure you guys are so excited. What was that? Was that an accident? Okay, no problem. All right. So now we're going to move on to word problems, which I really don't mind logistic word problems. I don't mind log or exponential word problems because we get to use our calculators, and our calculators are our friends. All right. So let's look at this first example. It says the population of deer after T years in Cedar State Park is modeled by the function P of T is equal to 1001 over 1 plus 90e raised to the negative 0.2 times T. What is the initial population of the deer? Yes, how'd you get that, Andrew? Let's see if I can't do this again. Okay. Yes. All right. So this time we're given an x value. What x value are we? Okay. What x value is it talking about? Or in this case, t. What t value is it talking about? What is our time at the start? 0. So what it wants to know, when t is equal to 0, what is your population? So what you do, you put your function into your calculator. So 1001 divided by 1 plus 90e raised to negative 0.2 times x. So that's our function. And we want to know when x is 0, what is our population? So on your calculators, I like graphing calculators more because we can just boom look at our table. Now on our table, what you're looking for is when x is 0. When x is 0, our y value is 11, meaning the population is 11. So what we did was plug into y1 or Desmos, and then we're looking on our table for when x is 0.
Is the y-intercept or the initial value always going to be c over 1 plus a, or c over 1 plus a? Because if you just drop the et to the power negative 0.2x, this gives you the 11 y-intercept.
Yes, because, yes, it is. Because time being 0, e raised to the power of 0 is 1. Exactly. All right.
So it's always safe to just...
Always. Yes. Yes. Very good. Yes. Personally, I found it easier to plug in to T. Okay. Do you, Arnon? Do you? Next, we have approximately when will the number of deer be 600? This time, they're giving us a population and wanting us to find time. So this is when we take this 600 and we plug into y2, or you plug it in as a separate equation in Desmos. We want to know where these two lines intersect. Oh my, I have to zoom way out and zoom way back in. So our logistic function and the 600 line intersect when x, or when our time, is 24.514. What is that? What is the years? Again, to do this on your calculator, now this one I actually did have. This is the actual example. In my calculator, I have my function in y1, and then I have 600 in y2. I go to my graph, and I'm trying to figure out where do those two lines intersect. So you press second trace, and you go to 5 intersect, and you press enter, enter, enter. And the x value is your answer. Any questions there? Okay. And then lastly,
1,001.
yes, Ruby, yes. What is the maximum number of deer possible in the park? We've already gone over this a couple of times now, or I've already said it or referred to it a couple of times. What is the maximum possible population in this example?
C.
Your C value, your carrying capacity, 100 or 100. Oh my goodness. 1001. Our carrying capacity. Our asymptote, right? Oh, carrying capacity. I said asymptote, was about to write asymptote. Any questions on this problem? Okay, so give me a second. In this example number 2, am I going to type in 1900 as x1, as my first x value? Yes. In our problem, it says T is years since 1900. So right here, our very first T, 1900 is 0 years since 1900. What about the second T? What's that? 10. Yes, you guys got it. 10, 20. I'm not going to list them all. So that's what I'm going to put in here. 0, 10, 20. And yes, you do have to put them all. 30. What's up? Yeah. Okay, so there they all are. Now I'm going to enter in my y values. 7.3, 9.1, 10.3, 12.6, 13.5, 14.8, 16, 0.8, 18.2. Okay. And then on Desmos, entering all of those in will automatically give you your answer. Is it number 9 on stat edit? No. No, that's linear regression. I'm sorry, linear. Oh my gosh. That is LN regression. That is the inverse of what you're trying to find. You need to go to B. You need to go to B on your calculator. It'll just say logistic. Logistic. Okay, so we have, if we were using Desmos, we have already found our equation. F of x equals, now our A value is 19.8749. On Math Excel, a lot of times it wants you to round to the 10,000s place, so I am going to put 4 decimal places out here. 19.8749 over 1 plus 1.7503 e raised to the power of negative 0.0350 times t. I believe that Math Excel on this one shoot, I don't know which one it is. But Math Excel will ask a few more problems. It will ask, okay, given this equation, when will the population reach like 15 million? And all you would have to do is in your second y equals. Oh, that's what I was trying to say. Okay. On your calculator. And I don't know how to do it in Desmos. I don't think that you have to do it because it already creates the equation for you. But on your calculator, if you're going to have to do further things using this equation you created, when you hit B, so you entered everything in your calculator and you hit B on stat calc, it brings you to this screen. If you store the equation, so you go down to the 4th thing, the store regression equation, if you click bars and go over to y bars and hit function, it'll bring you to this list of y's. You press enter, and now it will store the equation for you in your y equals. So you don't have to go and retype it all in. It's just a shortcut. You don't have to use it. But that's how you can store it so that you can later on go in and work with the equation a little bit. Wait, what? So when you go to stat calc and you go up to B, logistic, and you're on this page, you go down to store reg equation. Now another way you can do it besides hitting vars, if you hit alpha trace, it will also pull up the y's. Hit enter to put it in Y1. So that's what it should look like. And then hit calculate. And it will automatically store it in your y equals. My mind has been blown. No math teacher ever showed you that? I'm so sorry. But in this problem, however, it wants to know, when will the population of New York exceed 25 million people? So yes, you could go in and you could, okay, say, when will it go over 25 million, right? So you could put in y equals 25 because these numbers are in millions. So this 7.3 actually is 7.3 million people. However, our top number, our carrying capacity, is 19.87 million. That's as much population as we can have. 19.87 is less than 25. What does that mean? Yes, it will never reach 25 million people. Never. Okay.